Hello everyone, and welcome back to this exploration of complex analysis, and today we're going to be beginning our journey in the realm of integration, in the realm of the complex plane, which is quite different than that compared to the real world. So, what are we going to do? So let's assume that we have some path C that's a subset of the complex plane C, and let's assume that A and B are both complex numbers. Right? So what we want to do is we want to integrate some function. Let's assume that f maps C to C, and let's assume that we want to integrate f along that path C with respect to z, where z is equal to x plus iy, which are the real and imaginary parts of z. So our goal today is to see if we can assign a way to always calculate the integral of a complex valued function, provided that that function is even integrable in the complex sense, right? So that's what we aim to do today. So let's start off with a couple observations. Let's first off note that C is very similar to R2. So that means the integral over some path C of f of z dz should be similar. It should be similar to one of the following objects, and it should be similar to evaluating, let's say. I think that would be a more safer way to say it. So evaluating, let's say, the integral of a scalar function, let's say f of xy, with respect to the length of that contour. So where L is equal to the length of C, provided that that path is measurable, of course. Or we could say that it's equivalent to the integral over some vector field, say f of xy, dot product with du, where u is the parametrization of the path C. All right, so we have a couple options to consider to try and build a parallel between R2 and the realm of C. So what is the difference between these? Well, keep in mind that this particular integral is just equal to the integral of f evaluated at u of t times the absolute value of the velocity vector with respect to time, where a and b represents the bounds of your parametrization t, right? So in this particular expression, the direction for which you integrate or parametrize that path doesn't matter. So we should ask ourselves, should the direction matter for this? Well, in the real world, direction definitely does matter, because if you integrate from 5 to 2 or integrate from 2 to 5, you should get opposite answers from one another. So that would lead us to believe that the integral of a vector field, or the line integral of a vector field, should match more nicely or in parallel to that of integration in the complex plane. And eventually we're going to see that these formulas are actually very, very similar to one another, because if we parametrize xy with respect to u, then what we're going to have is the integral from a to b of capital F of u of t dot product with the velocity vector u prime of t dt. And we're going to see that integration in the complex plane is actually very similar to the line integral of a vector field. All right, so let's build a couple formalities before we actually get into that particular world. So let's start off by supposing that u of t is a reasonable parametrization of our path C. And then let's start off with our first definition. So we say that C, our path, is smooth if u prime of t exists for all t belonging to the open interval AB and continuous. And we're talking about the derivative of u. And it's continuous for all t belonging to the closed interval A and B. And there's going to be two parametrizations that are going to be very, very common in the realm of integration of complex functions. Right, so two parametrizations will be important. parametrizations will be important. And what are they? You want to take a guess? Important. The first of these parametrizations will be probably one of the most simplest paths of them all, and that would be a line. Right, so a linear path. And keep in mind, we're talking about linear paths in C. And the second path, you want to take a guess, this is going to have some curvature. These will be circular paths. And again, we're talking about circular paths in C. So how do you parametrize linear paths and how do you parametrize circular paths? Because you have to be comfortable with these parametrizations very, very well. So the parametrization for linear path is going to be equal to u of t. This is one of many ways. It's going to be equal to z of c plus r e to the it, where t is going to range from, that's going to be a circular path. Let's put that down here. Because remember, e to the it is cosine theta plus I sine theta. Right, so u of t is equal to z of c plus r e to the it, where t ranges from theta 1 to theta 2. So if you want a full circle, you can go from 0 to 2 pi or minus pi to pi. Either way is perfectly fine. Where this z of c value, that's the center of the circle, and this r is the radius of the circle. And for linear paths, there's a few ways you could go about this. I'll give you my favorite one. ZA times 1 minus t plus ZB times t. And here t will range from 0 to 1. So to get a sense of what this parametrization is doing, if you have 2 points, and I've notated them as ZA and ZB, what this does is traverse along the linear path connecting them from A to B. So this is located when t is equal to 0, and this is located when t is equal to 1. And I highly suggest you check those just to make sure these things are right. And for the circular path, let's draw a picture for that one. So our ZC is going to be located, let's assume that this is our center of our circle. And let's assume we have a point of reference, a horizontal line. Let's assume that this is theta 1. And let's assume that this is, let's assume theta 2. And let's assume that this distance is r. All right, so this distance right here will be r. And then what this traces, u of t, is it traces from here to here. So this is u of t, and this right here is your u of t for our linear path. All right, so those are going to be your common parametrizations. Yes, you can parametrize several other curves, but these are going to be the most two common ones that you're going to be dealing with in the complex plane. All right, so another note that I want to mention before getting into it, direction of the parametrization does matter. Even in the realm of real analysis, it mattered, because remember, if we integrate from 1 to x of 1 over t dt, that's going to give us the natural log of x. And if we integrate from x to 1 of 1 over t dt, that's going to give us negative natural log of x, right? So they're obviously going to be different values. So this and this obviously are different, provided that, you know, x is not equal to 1, because then they're both equal to 0. But in general, they're going to give you completely different answers, right? So with these things in mind, let us now define what it means for a function in the complex plane to be integrable. All right, so let's assume that f is going to map c to c, so c is going to be the domain. And let's assume that it's defined for all z belonging to c, where c is a subset of c, with c a smooth path. right? Then we say that f is integrable along C, or on C. I'll say along C. Along C, if there exists some number L in the complex plane. This is going to obviously be representable by a limit, similar to Riemann sums, such that the limits as n goes to infinity of the sum from k is equal to 1 to n of f of zk delta zk is equal to L, and this has to be true for all tag partitions of C. So this is just a truncated version of the definition of what it means to be Riemann integrable along C. So let me just briefly go over this definition just to make sure you understand what it means. All right. So let's assume that we have some path here. Let's assume that it goes from A to B. And what you need to do is you need to truncate this path into n regions. All right. So this is going to be the first partition, the second partition, the third partition, the fourth, the fifth, the sixth, and then the seventh. So we're going to have n sub-intervals of this path C, which is going to have n plus 1 points in this realm. And then you need to tag those partitions. So for example, that would be Z1, that would be Z2, that would be Z3, Z4, Z5, Z6, Z7. And then keep in mind these deltas need not be the same. For example, this would be delta Z1, this would be delta Z2, the length of those, and they don't have to be linear lengths. But as these lengths get close to 0, and then you project the length times the width and sum them up in order to get area, it should converge to a number L in the realm of the complex plane. So this still is baiting at the idea of Riemann sums and areas under curves, right? And keep in mind this has to be true for any tagged partition of that path C. Now, one very obvious result that we can get immediately from the definition of integrability is that if f is continuous on C, then f will be integrable on C. Obviously, that means if f is differentiable on C, moreover, if f is analytic on C, then f will be integrable on C as well. Now, obviously, if f is not continuous, that does not necessarily mean it's not integrable, but if it is continuous, this will guarantee integrability. Now, are there going to be similar properties to integrals of functions on the computational side that we had in the single variable calculus realm? The answer obviously will be yes. So let's just state that some properties of integration will still hold in the realm of the complex plane. I'll state two of the many. The first is the linearity result, so the integral along some path C of a f of z plus or minus b g of z dz. This will be equal to a, provided a and b are constants, of c of f of z dz plus or minus b times the integral over c of g of z dz, provided that f and z are integrable on C. Right, so complex integrals will still be linear operators, so this is a very useful property. And the integral along C of f of z dz will be equal to minus the integral of c prime of f of z dz. And what is the relationship between c and c prime? Well, c prime is the same points as c, but traversed in the opposite direction. And this property is analogous to the property that the integral from a to b of f is equal to the negative integral from b to a of f in the real world, in case you're curious. Right? So if we look at this in the complex plane, so let's assume we have two contours. Let's assume that this is C. And let's assume that this is C prime. So C and C prime. Notice that these curves look the same, provided that it's drawn to scale. But let's assume that C is traversed in the counterclockwise direction. So C prime will be traversed in the other direction, the clockwise direction. All right, so those are some of the basics that you definitely know when it comes to complex integration. Now let's get into other details. So up to this point, we have a couple basic theorems that tells us when a function is potentially integrable, but it doesn't really give us a way to actually find what those integrals are. We already know how to do integrals in the real variable world, so maybe if we can create a parallel between R, R2, and C, maybe we can then find a nice way to integrate in the realm of the complex plane. So let's assume that we have some function f that originally maps C to C, but let's parameterize it in such a way that f now sends a particular number that's real, let's call it t, to a complex number z. So the same exact range, just in some sense a parameterization of it. Let's also assume that f has a real imaginary decomposition of u plus iv as usual. So if we integrate a to b of f of t dt. Now keep in mind this will have complex numbers as outputs now, but keep in mind t is a real number, so I plug in a real number. I get a complex number back, which will then have a real imaginary decomposition. T is still a real number, so we're still integrating with respect to a real variable, so nothing is different on that end. So if we represent f in terms of u plus iv, then this is going to be equal to the integral from a to b of u of t plus iv of t dt. And why is that? Well, if f is parameterized with respect to t, its real and imaginary parts will also be parameterized with respect to t as well. And since we know that integrals are linear operators even in the complex plane, but here we're working in the real case, I is just a constant, then what we're going to have is the integral from a to b of u of t dt plus I times the integral from a to b of v of t dt. So what exactly do we have here? So we have this object here, and we have this object here. And keep in mind, u and v are technically in the realm of r, right? Because that's with respect to r, that's with respect to r. So both of these are real analysis type integrals. So this expression is well defined. So if we can parameterize f with respect to a parameter, and keep in mind that parameterization is usually with respect to the path C that we're integrating across in C, then we can pretty much perform the same exact rules and theories and tricks that we had in real analysis. So if this is indeed the case, then I invite you to try and verify that if the derivative of capital F is equal to little f, that is, little f is the derivative of f, so that means capital F is the antiderivative of little f, then what we're going to have is the integral from a to b of little f of t dt will be equal to capital F of b minus capital F of a. So this pretty much is our fundamental theorem of calculus result that we had before. And why is that the case? Well, because we're working in the real variable world, we're just going to have a real and imaginary part decomposition for both f and its antiderivative capital F as well. All right. Now, what is so special about this result? So keep in mind this result also applied to line integrals of conservative vector fields. In particular in R2. And this is extremely important. So if you don't remember vector fields and what conservative vector fields are, let me just give you a quick reminder. So again, we have the integral of a vector field over some path C du, where u is a parameterization, can be found in a parameterization way, the integral from a to b of f of u of t times, or the dot product, with u prime of t dt. So vector dot product vector is a scalar function, and then you integrate that with respect to time, and that's it. And if this field f is conservative, So what does it mean to be a conservative vector field? So if you don't remember what that means, so f is conservative if there exists some function f such that the gradient of little f is equal to capital F, right? That is, there exists a function or an antiderivative of that function capital F, right? So f in some sense is the R2 antiderivative of capital F, right? So if it is conservative, then this will be equal to f of b minus f of a. F of b minus f of a. Right? So once we have that, then that is, usually we say it's independent of path. And let me just draw a little picture in case you don't remember what's so special about this. So if we have some conservative vector field, if you remember anything about the curl of a vector field, if the curl is equal to 0, then we have a conservative vector field. And if we have some path, say here to here, right, we can integrate along that path C1, integrate along that path C2, and as long as the endpoints match, then the line integral over C1 of f times du1 will be equal to the integral across C2 of f and du2, where u1 and u2 are the corresponding parametrization of C1 and C2 respectively. Right? So once we have that, then we can actually just focus on the endpoints, evaluate the antiderivative there, and then subtract. Right? So we clearly see some parallels between complex variable integration and integration in the realm of R2. So what can we say with this? So connecting these two objects, we can then come up with the following theorem and then use the definition of a Riemann sum approach for integrability for complex variables and get a very, very important result. And it says the following. If we want to integrate a function f that maps c to c along some path c, then this will be equal to the integral from a to b of f u of t times u prime of t dt, where f is continuous on that path c, and u a reasonable parametrization of c for t belonging to a to b, and also c should be smooth. Now, if c is not a smooth path, you need not worry. So if we're in the realm of the complex plane, let's assume that this is the real part of z, the imaginary part of z, and let's assume that your contour has some corners on it. Right, so let's assume that's your c. All you have to do is just break up this contour into smooth pieces. For example, we can do C1 to be equal to this. We can do C2 to be equal to that. We can do C3 to be equal to that. And then by the properties of integrations and sets, then the integral over f over c will be equal to the integral of c1 plus the integral of c2 plus the integral of c3 for that particular function f, and you'll get the same answer. And of course, these paths c1, c2, c3 are indeed smooth. So if the path is not necessarily smooth, it can most of the time be decomposed into a union of smooth paths. So do not worry about that. Now that we have our first major result for how to integrate complex valued functions, let's take a look at a very basic but very important example, in particular f of z is equal to z to the power of n, where n is a natural number, and let's assume that c is a circle of radius r, that's positive, centered at the origin 0, 0. So how are we going to go about this? So if we want to integrate this particular complex valued function, we have to first analyze our contour. So our contour is going to be a circle of radius r, and let's assume that we're going to parametrize this counterclockwise, which is typically going to be the default for most parametrizations, with a couple exceptions here and there. All right, so there's our contour. And how do we parametrize that with respect to t? Well, we can let u of t be equal to r e to the it, where t ranges from 0 to 2 pi. So if this is u of t, then the derivative with respect to time is going to be equal to IR e to the IT, and t will still range from 0 to 2 pi. So now that we have our parametrization of the contour for which we want to integrate across, in particular we want to integrate along C of z to the power of m dz, then what will this be? So we're going to integrate from our boundaries for our parametrization 2t, then we're going to replace z, because f of z will turn into f of u of t, so we're just going to replace z with our parametrization. So we're going to have r e to the it to the power of m, multiplied by the derivative of our parametrization, ir e to the it dt. Right? Now we have just a basic integral that we should be able to work with. So what are we going to have? So we have an I, so we can factor that out. We have a couple r's. We have r to the power of n here and r to the power of 1 there. So we're going to have r to the power of m plus 1 on the exterior, times the integral from 0 to 2 pi. And what are we going to be left with? So we have a couple exponential terms here. So we can write that as e to the power of I and then m plus 1 to the power of t dt. And then we can use our chain rule for antiderivatives and differentiation. And this is going to be equal to what? So this will be equal to I r to the power of m plus 1 multiplied by 1 divided by m plus 1 times e to the power of I m plus 1 t. And then t needs to range from 2 pi to 0. Right? So we are only going to have one issue, and that's when n is equal to -1. So when n is not equal to -1, this is going to be equal to IR m plus 1 all over m plus 1. And then what we're going to have here is what? So we're going to plug in 2t into here, and keep in mind n is a natural number, so these are just integer multiples of 2 pi I. Right? And you should know that that's going to be equal to 0. And when you plug in 0, that's also going to be equal to 0. So that's going to be equal to 1 minus 1, which is going to be equal to 0. So actually, let's write that as 1 minus 1, 1 minus 1, and that will be equal to 0. Now, what about when n is equal to positive 1? So if n, or negative 1. So if n is equal to -1, then our integral is equal to the integral from 0 to 2 pi of r to the power of -1 e to the minus it times ir e to the it. And then that's going to be dt. Notice that our e to the it and e to the minus it will cancel each other out. And we're going to have r to the minus 1 and r. And keep in mind, r is not equal to 0. R is positive, so they're going to cancel out. And then we're just going to be left with the integral from 0 to 2 pi of I dt. And that's just going to be equal to 2 pi I. So therefore, we can summarize this result in the following compact way. And this I highly recommend you memorize. So the integral over a circle centered at the origin of radius r, dz, is equal to 0, provided that n is not equal to -1, and it's going to be equal to 2 pi I if n is equal to -1. So the only issue that we have here, so we can summarize, for example, if we have the integral over c of z to the power of 4, this is going to be equal to 0. If we have the integral over c of 1 over z to the power of 5, that's going to be equal to 0. And if we have the integral over c of 1 over z, this is going to be equal to 2 pi I, right? And you have the several other integers that you could consider, right? So that's actually very interesting, but eventually you're going to see that this is going to be a very powerful result for integrating some more complex or complicated valued functions. Now, let me start off or end with the following theorem, and then I'll do an example of it. And it says the following. If C is a closed, positively oriented contour, such as a circle, centered at or potentially enclosing in its interior, z naught, then we have the following result. Now, I will not prove the general positively oriented contour or the enclosed in its interior part, but if it's a circle centered at this particular point z naught, then you should be able to prove this very nice formula. And it's just a generalization of the last one we just proved. So the integral over c of z minus z naught to the power of n dz, where again n is a natural number, will again be equal to 0 if n is not equal to minus 1 and 2 pi I of n is equal to minus 1. Eventually we're going to prove that it doesn't really matter that it's a circle. So as long as you have some path c that's closed and positively oriented, and the center zc, or z naught, is located on the interior of that closed contour, this integral will be equal to 0 as long as that power is not equal to -1, and if it is -1, then it's going to be 2 pi I. All right, so that's a very interesting result. Now, do we have to integrate over closed boundaries? No, of course not. We can integrate over lines if we really want to. So let's actually do a quick example of that. And let's just do a basic line. Let's do from here to here. So from 0 to 1 plus I. And let's assume that we want to traverse outwards. And let's assume that's our C. So how would you parametrize that? So u of t will be equal to 0 times 1 minus t plus 1 plus I to t, which will be equal to 1 plus I times t, or you can write that as t plus it, and here t will range from 0 to 1. All right. So let's choose a particular function to integrate. So let's find the integral over this line c of z squared dz. So you might want to pause this video and see if you can do this on your own. So this will be equal to the integral from 0 to 1, our boundaries of t, and then we're going to have z squared. So it's the parametrization of z, so that would be equal to 1 plus I squared t squared times the derivative of this parametrization, which will just be 1 plus I, and then dt. So that's going to be equal to what? So that's going to be 1 plus I to the power of 3 times 1 over 3 t cubed, and here t is going to range from 1 to 0, and then subtract. So that's just going to be equal to what? So that's going to be 1/3 times 1 plus I to the power of 3, and doing your rotations of 1 plus I, because keep in mind, powers of complex numbers are just scalings and rotations, and keep in mind that the norm of 1 plus I will be equal to the square root of 2. So the norm of 1 plus I cubed will be equal to root 2 to the power of 3. So this will be equal to, once you simplify, 1/3 times minus 2 plus 2I, and then you can simplify to that to be negative 2/3 plus 2/3 I. Right? So that would be your result. So with these tools, you're able to start to explore the realm of complex integration by using parametrizations. Now, if you don't want to use parametrizations or the path is really complicated, yes, that can be a problem, but we will slowly build very important theorems that will make complex integration a little bit more easier to deal with. So I hope to see you in the next video, and I hope you enjoyed this one. Take care.